All right. Your team has now observed three star clusters: a young open cluster, an intermediate age open cluster, and an old globular cluster. In this video, I'm going to show you how to take all those images, put them together into well-made stacks, and then combine the stacks into a color image, a preliminary color image. We'll come back to it near the end of the module and make some further modifications. But first things first, and first thing always should be to check your images. Garbage in, garbage out. So let's look and see if we have any garbage images that we want to exclude from the analysis. So go to Skynet, go to the observation page, let the thumbnails load, and we're just going to quickly skim through them. Now, my target is an old globular cluster, NGC 3201, and I'm looking at them. Some of mine were taken with the Prompt Meckering telescope in Australia. Some were taken with the Prompt 5 telescope in Chile. Totally okay to combine these images from different telescopes. Looking at them, and all the thumbnails look very good. No problems. Well, what would a problem look like? The primary thing you're looking for is if you were clouded out. This picture on the left is typical of looking at clouds. Basically, if you're looking at clouds, you're of course not going to see your astronomical target. You get something that looks very much like one of our flats, just illuminating the whole sensor. You can see its manufacture pattern. You see how the sensor was scraped when it was made. You see out of focus dust. That's dust on the camera window, out of focus on the sensor. And if you see any of those, make note of the image number. We're going to want to exclude them from the analysis, not even load them in. Or if you've already loaded them in, to close them out. Now, the picture on the right is partial cloud cover, thin cloud cover. So we're looking through clouds, very thin clouds, but we can still see some of the astronomical object behind it. You can see here the out of focus dust, so it's kind of halfway in between. You can exclude these or you can include them. We have algorithms, you'll see, that get rid of questionable images. The more that we can get rid of ourselves at the beginning, the easier it is for the algorithm. So something like this on the left, definitely excluded. On the right, you could throw it in if you want and let the algorithm take it out, or you could just take it out from the get-go. Up to you. What else? Well, you may see an image with a ghost in it. This is a picture of a galaxy, and whoever used the telescope right before this image was taken looked at Jupiter. And so there's an image of Jupiter burned into the sensor, and it takes about 20 or 30 minutes to fade away. And you may think this image is ruined, but you can actually use this. As long as the ghost doesn't appear in the other images you took in this filter. You may remember we did a filter set, waited 30 minutes, repeated the filter set, waited 30 minutes, etc. This is because if some of them are contaminated by ghosts, hopefully the other ones aren't. And when we combine them, the algorithm's smart enough to say, oh, this one is not like the others. And it will remove it just at that pixel location. It will use the rest of the image, but where the ghost is, it will just use the other images. So if you have a ghost like this, it's okay. You can use it. What else can go wrong? Lots of things. Let me show you just a few. This upper left, the mount has stopped tracking. So it's not counteracting the rotation of the Earth, and all the stars are getting streaked. Can't use that. Here, wind is pushing on the telescope, streaking the stars. Probably don't want to use that. Here, the stars are out of focus. Don't want to use that either. In this row, we have a shutter that didn't close all the way. You see this line bleeding out from the star. Here we have a shutter that didn't open all the way, got stuck. Here we have a case where someone left the lights on in the dome, or the moon was too close. There we have a satellite moving through the image. If you have two of them, it's an airplane. There's a light on each wing. And here we actually have a bug in the system, a bug sitting on the camera window. And believe it or not, I've seen this 3 times in the history of Skynet. So it does happen. Other things can happen as well. What do you keep? What do you throw out? The rule of thumb is if you see well-focused stars, probably keep it. Like all these images down here on the bottom have well-focused stars. So that means we can use parts of the image. And we'll let the algorithm figure out what parts are good and what parts are bad. Up here, we do not have well-focused stars. Those you'll want to throw away. Okay. One other thing to check for before we go into Afterglow is, did you get a WCS with all of your images? Now, all these images have stars. If you have stars and enough stars, Skynet should be able to put a world coordinate system, a WCS, on the image. If it can't, you'll get a little yellow triangle, I think right here. And you hover over it, and it says it was not able to get WCS. So most likely, if you don't have a WCS, there weren't enough stars in the image, and you're probably looking at clouds and don't want to use it anyway. If it looks like a usable image, but doesn't have a WCS, make a mental note. We can try to add a WCS in Afterglow. Okay, let's go to Afterglow. So here I am in Afterglow. I've loaded all my images. And if you had any images that were bad, either don't load them in, or once you've loaded everything in, go through. You have the filter name and the exposure number, find the ones that were bad in Skynet, and just hit the X to remove them. Now, if any of them were missing a WCS, you can go to this tab right here, WCS calibration, select the ones that are missing a WCS, and only those ones, set it on plate solve, extract value from current viewer, and submit. Give it a second, and it may be able to add the WCS. If it can't, come over here, hit the X, and remove it. If it can, great, you can use it. Most likely, all of your images that are not clouded out will have a WCS. Okay, the image processing steps. First, go to cosmetic correction. We're going to use this tab, and this tab. The first one is cleaning, to remove defects in the image. I find this should be a good example. Here we go. Now, lots of stars, but also some stray bad pixels here, here, here. And so all you have to do, make sure you have nothing else in here. You know, before you get started, clear everything out. Just have the images you're working with. Select all and submit. This won't take long. It will go through, it will find bad columns in particular, and then bad pixels as well. It's almost done, 75%, 80%. Complete, and voila, those pixels disappeared. Very nice and clean. Okay. Now, the next thing we're going to do is align. So we go down to the Aligner tab. Again, we're going to select all the images. Mosaic mode should be off. We're not making a mosaic. The reference image, it doesn't really matter. Select one, the others will be aligned to it. Then, which of these do you turn on? Turn on crop. Basically, after it lines them all, it will crop them to just their overlap region, which is nice. Enable rotation. From image to image, the telescope is moving and gravity is pulling on it different, and you may have small rotations. So that will let you correct for that when it aligns. This next one, enable scale. If all your images were taken from the same telescope, all those images have the same scale and you don't need it. Now, in my case, the images were taken from different telescopes. And they have different scales. The pixels have different sizes. And the fields of view are different. So I'm going to enable scale. That allows some of them to be stretched out or shrunk down to match the reference image. Finally, you can disable skew. You don't need skew for this. Mode should be WCS. In previous exercises, like with the moon, we used feature-based alignment. With the planets, we did manual alignment, clicking on the planet. But here we can use the coordinate system. We have enough stars, we have a coordinate system, and we can use that coordinate system to match it all up. And this should go pretty quickly. So I'm going to hit submit. Okay, they're all aligned. Now, we're going to check them. Sometimes, particularly with a globular cluster or with a streaked image, if one of these images is streaked, you can get a bad WCS and a bad alignment. So let's do the following. And we've done this before. We did this in Module 1D with the planets. Come over here to the Workbench Settings tab. Turn on Sync Orientations. It should be sky. We have a sky coordinate system, a WCS on each one. Okay, go back to your file list. Go to the first one. Zoom in to some of the stars. And then using Shift Arrow, we're going to load them all in. We have 20 of them. Should not take long. It's actually not loading the whole image, just the zoomed in area. That speeds it up a bit. Okay, I'm at the end. Now I have them all in. I'm going to just go through and make sure they all are aligned. Ah, see that one? That one did not line. It looks kind of streaked. So the last B1, let's check the others. So they're all good except for that one. Let's B16. If it didn't align well, just remove it. Odds are all of yours aligned. But if you have a bad one, it's best to remove it. When we're stacking these, we only have 5 images. That's not a lot. And so as much help as we can give it, the better the stacks will be. Later on in the course, when you're stacking 20 or 30 images, it has more to go on and has an easier time finding and throwing away the bad ones on its own. Okay, so I'm now down to 4 B images, but I have 5 of the other ones. Okay, we're gonna go to stacking. It's this tab here. And first, I'm going to filter on one of them. I did _B_, so I'm just looking at my 4 remaining B images. Filter on that, and then I can select all. See, it just selects those 4 because I filtered on them first. Now, I have some settings here that you're going to want to replicate. Mode is set to average. It's going to average those 4 images together. And that's good. When you're averaging, you're increasing the signal to noise. The noise is random. And so in some it may be high, and some it will be low. I average it together. It cancels out somewhat. We call this beating down the noise. But the stars, they're there in all of them. That's the signal. Signal stays the same. The noise decreases. You're increasing your signal to noise. That's what you want. You want a high signal to noise. You get that by combining more images. You get better signal to noise. So averaging, that's the key thing in stacking. is to increase the signal to noise. But there's some other things we can do at the same time. One is rejection. For example, that ghost. Suppose it's in one of these images, but not the others. So when it comes to the point of averaging that pixel where the ghost is, it will compare it to the values in the other three images and say, wait, this thing is not like the others. I'm not going to use it. I'll just use the others. So it will go through all the pixels and not just average them, but check and see if anything is outlying and remove it. And so set rejection to Chauvenet. It's an outlier rejection algorithm. It's kind of like, well, it is sigma clipping. You may not know what sigma clipping is. Think of it this way. Suppose your class has a grade distribution. Maybe the average score was 50, and the standard deviation was 5. So most people got, between 40 and 60 points. But suppose some person got 130 points and another person got 1 point. Those people are going to blow the curve. They're definitely outliers. And so this is a way to identify them. There are so many standard deviations from the average. We're just not going to include them. Something weird is going on. Maybe one student was super smart, or maybe that student cheated. Maybe the other student, I don't know, filled in the bubbles wrong, etc. So set rejection to Chauvenet. Set low to 1 and high to 1. This is basically turning on. I'll reject things that are low. I'll reject things that are high. And then finally set scaling to histogram. Each of these images actually have a different level depending upon the efficiency of the telescope, how much atmosphere it was looking through at the time, thin cloud cover. So you got to put them all on the same level before you look for outliers. Histogram is the best way to do that. Let me show you some examples of this. Here's a great example. Here I have 25 images and I aligned them. But in this case, I didn't clean them. They have a bunch of bad pixels, hot pixels, cold pixels, and I didn't clean them. Let's say I had 10 of them in this little piece of the image. After aligning, all the other ones get shifted around. So all those bad pixels get shifted around. If I have 25 images, 10 bad pixels, I now have 250 bad pixels, and they're all over the place, totally messing up the image. Now, we got rid of most of them by cleaning, but not all of them. Some remain. But Chauvenet rejection gives you this. It was able to figure out with each one, this one is not like what I see in the other images, so I'm not going to use it in the average, and you get a much cleaner image. Here's that whole image. So what I did here, again, it's 25 images. In this case, I had 20 good ones and 5 where I was just imaging clouds. And I should have removed those 5. But I didn't, just to show the power of the algorithm. You can kind of see the bright background and see the patterning. Those are those 5 bad images. If I turn on Chauvenet rejection, it removes a lot of that. This has a brighter background than this. Doesn't remove it completely, but it removes a lot of it. So it's good at removing little defects, but also it can help remove broad defects. Now, what's this smart stacking? Wouldn't it be nice if one image was just so much worse than the others, we just didn't include it? And we tried to do that manually. When you peruse them with your eye, you said, oh, that one's bad, I'm going to throw it out. But maybe some bad ones snuck in. So what smart stacking does is it says, this is your worst image. I've stacked them all, but now I'm going to do it again. I'm going to stack them all minus that bad image. And if the stack is better, I'm going to throw it away. And then it checks the next one and the next one. So smart stacking is a mechanism to throw out not just bad pixels, bad places, but entire images. Back to our example here. Here it is with smart stacking turned on as well. See how dark the background's gotten? This was original with 5 of them, just images of clouds. Chauvinet rejection helps a little bit, and then smart stacking really helps. It just threw out those 5 images. So smart stacking, you want to turn that to SNR, trying to maximize the signal to noise. Make sure equalization is turned off. That's primarily for mosaics, but make sure propagate mask is turned on. When you cropped your images, that's called a mask. We put a mask around the boundary we don't want to see. And here we're pushing it along. So you want to propagate that mask. That makes that cropping move forward through the stacking stage. I'm going to submit. And this is only 4 images. It should go really fast. Now, I should say, if you're doing outlier rejection and smart stacking, it slows it down. It's not bad with 4 or 5 images. Later in the course, when you're doing many images, doing both of these can be a slow process, but it's worth it. Okay, now I got my V images. I just changed the filter, select all the settings are the same, submit. A little bit slower because it's 5 images this time. Okay, that one's done. R. And the last one we observed is I. It's not quite infrared, but it's almost infrared. Okay, let's take a look. I'm going to filter on the word stack. So there are my 4 stacks. Now, if you had an internet outage while that was being done, it came back with a different name, just file and a number. So if you're missing 1 or 2 because of internet dropouts, you can search on the word file and find those as well. So let's take a look at them. Here's B. This is my 4 Bs combined. That's a pretty good looking image. That's the I band. Here's the R band. There's the V band. Okay, we're going to select them all, go to the triple dots and group them. Okay, it's made a group. Let's get rid of the stack filter and find our group. Here it is. So that's the whole thing grouped together. Now, let's turn off the I band. We got the B, the I, the R, the V. We're going to combine the B, the R, and the V into a color image. The I, all of them we're going to extract photometry from in the next video. But just to make the image, let's turn off the I band. You can hide it by clicking on the eyeball there. So the I is no longer part of it. Let's color the other layers. Right-click on the B, color it blue. Right-click on the R, color it red. Right-click on the V, and we're going to color that green. Okay, so we have a preliminary image here. We got some red stars, some blue stars, but we can make this a lot better. And that's the last part of this video, how to set your display settings. Okay, so I'm going to go to display settings, and the first thing I'm going to do before we get into any of this is I'm going to go to settings. and go to photometry. Here under aperture photometry, come down here and restore aperture photometry defaults. Particularly if you're doing some of the radio modules before this, you change the settings, optimizing them for radio photometry. We're back doing optical stuff now. So just set it back to regular settings before the next step. And we'll come back to this page in a second. Okay. Workbench. I'm in display settings, so here we go. This is very much like what we did with Uranus and Neptune. Pick one of the layers to be the reference. Doesn't really matter which one, not too much. Come to Color Composite Tools, and we're going to link all layers pixel value, not percentile. What we have right here is already kind of percentile, and the colors aren't quite right. With percentile, it's making an assumption. The assumption is the brightest thing in the image is white. The closer that is to true, the closer your colors will be to correct, but it's seldom perfectly true. And so the colors are a little bit off. Instead, we're going to use the stars themselves to calibrate the image. All these stars have been observed before. We know their brightnesses in blue, green, and red. So we can use them to set the levels correctly. So go to Link All Layers, Pixel Value, and initially this changes the colors. And it's kind of random. My red image had more counts, so I have a kind of reddish picture right now. These are uncalibrated colors, and we're going to go forward and calibrate them. So to calibrate, come down here to Photometric Calibration, click on it. Sometimes it fills them in for you, sometimes not. You may have to do it yourself. So the red one goes first, then your green stack, and then your blue stack, and then press this button, measure 0 points with field calibration. You come down here, you see it's working. What it's doing is it's extracting all the stars in your image. It's comparing them to a catalog, in this case, the APAS catalog. And that's letting us know if one of the layers, the counts are too high or too low. And that's what these numbers are. These are called the 0 points. They're magnitudes, but they're setting the relative levels of the red, green, and blue layers. You have to pick a reference layer. It doesn't really matter which one. The next thing is called white balance. We'll learn more about this in Module 4. Basically, the human eye sees a black body that peaks in the B band, in the blue band. The human brain interprets that as white, strangely enough. A black body that peaks in the blue band, B, the human brain thinks that's white. And so that's important. If we want the colors to look right to the human brain, we have to build that in. This bit here is for reddening by dust. There is dust between us and our target. Not so much this particular one, but for many of them, including your open clusters especially, there's dust. The open clusters are in the plane of the galaxy. We're looking through dust, and dust reddens your colors. You can use this to de-redden. We just don't know by how much yet. By the end of the module, we will. Right now, just leave that at 0, and this will give you the colors that you would see from here on Earth, looking through a telescope, looking through all the dust. What colors do you see? Lastly, you want neutralized background on. The background can sometimes have a residual color. After all, the sky is blue. Particularly on a moonlit night, there may be some blue in the background. Or maybe you have a bad flat that can add some color. That neutralized background keeps the background black. Okay. Calibrate. Now we have natural colors. These are the natural colors of the stars. Okay, cool. But before we finish, let's improve the image. Let's play with the brightness and contrast settings. Many of these stars are blown out. See how it just kind of gets white? They're all chopped off. It's not because we exposed too long. It's just because how the brightness and contrast are set. And so we're going to come down here and change the stretch mode. It's currently in linear. The first four are simple stretch modes. You can see the faint end, but you blow out the bright end. Or you can see the bright end, but you don't see the faint end. This last one, midtone, is fancy. Let me show you here. Let me slide this over and make some space. For the simple ones, you have a background level and a saturation level. If I pick midtone, we have three. We have a background level, a saturation level, and an extra thing in the middle to control. It's called a control point. Now, after you change the stretch, you want to hit default again. And look at that. Isn't that better? We can still see the faint stuff, but the bright stuff is not blown out. It's like a magic, it's magical button. Now, to adjust this, the primary thing you want to adjust is the midtone level. If your image is particularly noisy, you can hide that noise by increasing. Let's go up to 99. See, it dims everything, which also hides the noise in the image, or 99.9. At this point, I'm losing stars. So I'm actually going to go the other way. Let's go down to 90. That brings out lots and lots of stars. It really depends on your image. Sometimes you want to raise the midtone level, hide the noise. Sometimes you want to lower it and bring out more stars. Now, the other thing you can control is the background level. It's currently at 1. If I move it up to 10, basically it's taking the faintest 10% of pixels in the image and making it black. So it's a great way to darken the background. Here, I'll go back to 1. See, the background's kind of bright. There's 10% is darker. Now you can get extreme. There's 50%. It looks good at this scale, nice and dark, but if you zoom in, it looks over-processed. If you raise the background too much, you get this over-processed feel where it just drops immediately into blackness. I'll go back down to 10. I'll probably go with 10. Both of these, the midtone level, the background level, it's aesthetics. And you'll get a feel for what looks good and what doesn't, and what looks good and doesn't to you. Okay. Then you just want to save this. Come over here to the group, save file, and go to Files, Workspace, and you can save it here. Actually, already have a copy saved. Okay. And then export it. Don't use the viewer snapshot. It only shows you what's in the viewer. You may be losing pixels. Use this one right here, export images JPEG. So here it is. And you may want to Google this target, get an idea. Actually, it looks fairly well-oriented, I think. Often with these, you have to do a flip. Let me see if a flip helps here. Nope, I think it was actually right before. Yeah, okay. So match it up, and you can crop it as you see fit. And then save it. You don't want to play with any color settings because you work very hard to get natural colors. So you want to keep that. Okay, this is your initial image.